So hi guys, for today's video we'll be starting off with the first law of thermodynamics, which states that no energy is created nor destroyed, meaning that the energy is conserved all throughout the chemical reaction. Now it also involves the internal energy, which is the sum of the internal energy plus the work done or given by the surroundings or to the surroundings. So let's start. Anyways, so let's first answer number 1. The work done to compress a gas is 47 joules. As a result, 93.7 joules is given off to the surroundings. Calculate the change in internal energy of the gas. Now, the equation that we'll be using is very simple. We have this one. Okay. We have internal energy is equal to Q plus work. This is it. Now, according to here, that the work done to compress a gas is 47 joules. Now, the work done to compress a gas is 47 joules. We need to classify if this is a positive work or negative work. Now, based from the keywords, it says compress, meaning that the surroundings is the one doing the work to the system. So, when the work is done by the system, that means that the work is positive. However, if the work was done on the system, we'll get a negative work. So this is negative work is positive 47 because it received work from the surroundings. Now for Q, 93 joules of heat is given off to the surroundings, so meaning this is a negative heat since it's given off to the surroundings, so meaning that the system is doing is giving heat to the surroundings, so it's negative 93. So we'll plug it in. So I hope you can still see it, guys. Delta E is equal to negative 93 joules plus 47. Now using our calculator, negative 93 plus 47, that gives us negative 46 joules. So this is it. Now if you're asked whether if this reaction is exothermic or endothermic, so when your final answer is negative, it is exothermic, meaning that the heat is being released. If you got the final answer which is positive, that means you received work, or meaning the system absorbs work, or the system received the work or the heat. So that's endothermic. So in this case, since it's negative 46 joules, its classification or the classification of its reaction is exothermic. The heat is being released. Okay. Now let's proceed to the second problem. Okay. Calculate Q and determine whether heat is absorbed or released when a system does work on the surroundings. When a system does work on the surroundings equal to 64 joules, and the internal energy is equal to positive 213 joules. Okay. Anyways, let's go. Okay, guys. So I'm gonna transfer to another paper So again, I'm going to read the second problem. So calculate Q and determine whether heat is absorbed or released when a system does work on the surroundings, equal to 64 joules, and the internal energy is equal to positive 213 joules. Okay. Now, oh my days. Okay. Oops. So, again, the formula for the internal energy is equal to delta E is equal to Q plus work. In this case, we're gonna write the given. Okay, for this case, internal energy is given, which is positive 213 joules. Next is we have does work on the surroundings equal to 64 joules. Now, since the system does work on the surroundings, that means the work done is negative 64 joules. Negative 64 joules. Now we're asked to calculate Q and determine if the heat is absorbed or released by the system. So let's plug it in. It's equal to Q plus work. Now we're asked to find Q, so we're gonna subtract work both sides. I hate this. So negative work, so this cancels and this that remains Q remains, and therefore we get delta E minus work. So to solve for Q, just plug it in. Plus 213 joules, positive 213 joules, minus negative 64 joules. Our final answer for Q is equal to, using our calculator, positive 213 minus 64. That gives us a positive answer, 277 joules. In this case, we were asked to determine whether the heat is absorbed by the system or heat is released to the surroundings by the system. So our classification for this is heat is absorbed. So that's it for first law of thermodynamics. Now for the next part of our first FA is we are asked to calculate the delta H of the reaction for the following reaction. So this is enthalpy. So we all know that enthalpy is equal, wrong pen. Enthalpy is just equal to internal energy plus PV. If I got it right, enthalpy is equal to E plus PV. So this one is internal energy, this one is pressure, this one is the volume. Now we can actually calculate work in thermodynamics by using this formula, negative PV, delta PV. Oh, I'm sorry, I got the equation wrong. This is to calculate work for in thermodynamics. It's just equal to work is equal to negative P delta V. So this pressure is constant and the volume is just a change in volume. So the final volume minus the initial volume. Okay, so we're not going to discuss thoroughly on like the enthalpy, the whole equation of H plus PV. We're going to calculate the standard enthalpy reaction for SiO2 solid plus 4HF and SiF4 plus 2H2O. So let's go. So the first thing we're gonna do is we need to always remember that to calculate for the standard enthalpy of the reaction, standard enthalpy of a reaction, it's always the products minus the reactants. Okay? Nothing else. It's products minus the reactants. So our equation, the given equation was or is SiO2 solid plus 4HF is equal to SiF4 plus 2 water. So don't forget it states okay. So using your thermodynamic table of thermodynamic quantities, you can find the standard enthalpy formation of each reaction. So in this case, let's set up the equation first. So let's find first the standard enthalpy formation of each reaction. So for SiO2 solid, it's what do you call this? Negative 910.9 kilojoules per mole. For HF, this is negative 273 kilojoules per mole. For SiF4, it is what do you call this? It is negative 1614.9 kilojoules per mole, and water is negative 285.840. Okay, so many scholars daw guys, they tend to to get the standard enthalpy of the reaction wrong, since they subtracted reactants minus products. So always remember products minus reactants. That gives us the standard enthalpy formation of the standard enthalpy of the reaction. So let's start. So my technique, or the technique that Mom Guy taught us, is that we first place the standard enthalpy formation of each element at the top, and then when we solve for the standard enthalpy of the reaction, we just plug it in one by one. So we don't need if we're gonna put like all the standard enthalpy formations here at the very bottom, there is a possibility that the scholars or the students might subtract it altogether, which gives the answer very wrong, or the answer is still correct, the number is still correct, but the sign is different. So always remember it's products minus the reactants. Okay, so let's go for a while. Okay, in this case, so I hope you guys can still see it. So it's negative H reaction is equal to set this equation up. So again, always remember it's products minus reactants. So in this case, we're gonna use the molar coefficients, or the mole ratios, since at the same time this involves chemical equation or chemical reaction, and sometimes when we balance equation, there's always, or most probably, there's always the presence of molar coefficients. So let's start with the products minus the reactants. So SiF4, so it's understood as 1. That gives us negative 1614.9 kilojoules per mole. And next is plus water. We have 2 moles of water, and the standard enthalpy formation of that is negative 285.840 kilojoules per mole. And next is, of course, we subtract again, since it's products minus the reactants. So next is the SiO2. which is negative, oh, I'm sorry. 1 times negative 910.9 kilojoules per mole plus 4 moles of HF, negative 273 kilojoules per mole. Now, always remember to multiply each elements or each compounds by its molar coefficients so that you'll get the final answer correct. So it's very important, regardless if it's 1 or 2, the presence of molar coefficient is still there. So, using our calculator, that gives us, I'm sorry, 164.9 plus 2 negative 285.840 minus 110.9 plus 4 negative 273. So my final answer, or according to the calculator, it's negative 183.68. The unit is kilojoules. We're not yet done since we still need to consider the significant figures. So in this case, we are actually, we are actually using addition and subtraction in this part. So we're gonna use the, the given number, the given unit. So the smallest given, like the smallest unit, like, I hope you get it, and when it is addition, the least number of decimal places, and for multiplication or division, it's the least sig figs of the given. So in this case, this involves addition and subtraction, so we're gonna use the significant figures with the least decimal places. So in this case, the least significant and the least number of decimal places is negative 273 kilojoules per mole, because it is a whole number. So when you have a whole number and you're actually your final answer must be a whole number. When, for example, okay, a whole number plus decimal, your final answer must be whole number, since again, the significant figures for addition and subtraction must correspond to the least number of decimal places. So in this case, whole number doesn't have any decimal places, meaning we will get the final answer of a whole number. So in this case, we have negative 183. Our final answer must be negative 184 kilojoules. Boy, I hope you get a guess.